Numbers are the building blocks of mathematics. Among these numerical wonders lies a fascinating group known as real numbers. Real numbers encompass a vast spectrum of numerical values. Imagine a number line stretching infinitely in both directions. Every single point on that line represents a real number. Real numbers include familiar categories like integers, fractions, and decimals. Integers are whole numbers, both positive and negative, without any fractional parts. Fractions represent parts of a whole expressed as a ratio of two integers. Decimals provide a way to express numbers with fractional parts using a base 10 system. As we delve further, we'll encounter two fundamental types: rational and irrational numbers. Rational numbers, a fundamental subset of real numbers, are defined by their ability to be expressed as a ratio of two integers. This ratio, often denoted as PQ, where P and Q are integers and Q is not zero, forms the essence of rational numbers. Integers themselves can be considered rational numbers, as they can be represented as a ratio with a denominator of 1. When a rational number is expressed in decimal form, it either terminates or repeats in a predictable manner. For instance, 1/4 has a terminating decimal of 0.25, while 1/3 results in a repeating decimal of 0.333. Rational numbers hold immense significance in various mathematical operations. When we perform arithmetic operations on rational numbers, the result always remains within the realm of rational numbers. Their well-defined properties and predictable behavior make them indispensable tools for solving problems and modeling real-world phenomena. While rational numbers exhibit predictable decimal representations, irrational numbers present a captivating enigma. Irrational numbers cannot be expressed as a simple ratio of two integers. Their decimal representations neither terminate nor repeat in a predictable pattern. One of the most famous examples of an irrational number is pi, a mathematical constant representing the ratio of a circle's circumference to its diameter. Pi's decimal representation, approximately 3.14159, continues infinitely without any discernible pattern. Another well-known irrational number is the square root of 2, representing the length of the diagonal of a square with sides of unit length. The discovery of irrational numbers challenged the belief that all numbers could be neatly represented as fractions. Despite their chaotic decimal expansions, irrational numbers exhibit remarkable order and significance in various mathematical contexts. The number line is a powerful visual tool for understanding real numbers. Picture a line extending infinitely in both directions. We choose a point as our origin, representing 0. To the right, we mark positive integers. To the left, we mark negative integers. Rational numbers, like fractions, also find their place. Irrational numbers have specific positions too. The number line shows the order and magnitude of real numbers. Decimal representations provide a standardized way to express real numbers, allowing us to perform calculations and comparisons with ease. Understanding the nuances of decimal expansions is crucial for grasping the nature of both rational and irrational numbers. As we explored earlier, rational numbers exhibit terminating or repeating decimal representations. Terminating decimals, like 0.25 or 3.75, have a finite number of digits after the decimal point. Repeating decimals feature a block of digits that repeats infinitely, often denoted by placing a bar over the repeating digits, such as 0.333. Irrational numbers possess decimal representations that neither terminate nor repeat in a predictable pattern. For instance, the decimal representation of pi is 3.141592653589793. The distinction between terminating repeating decimals and non-terminating non-repeating decimals forms a fundamental concept in understanding the difference between rational and irrational numbers. Decimal representations provide a practical and standardized way to represent real numbers, facilitating calculations and comparisons. Real numbers are more than abstract concepts. They form the backbone of our understanding of the universe. From basic measurements to sophisticated calculations, real numbers provide the numerical framework for our world. In science and engineering, they are essential for measuring, modeling, and designing. Whether calculating rocket trajectories or predicting weather, real numbers are the language of scientific inquiry. In finance, they represent monetary values, track stock prices, and calculate interest rates. These applications highlight their practical importance in our daily lives. Studying real numbers lays the foundation for advanced math and understanding our world.